Okay, so let me enlarge this to the screen view, and we will talk about the power spectrum and about spectral estimation. Now, we'll talk a lot more about spectral estimation later on in the course, but just want to introduce the concept now while we've been discussing the power spectrum. So basically, the power spectrum can be found from the Fourier transform, where in this equation x of f represents the Fourier transform, where f is frequency in hertz. So we're just taking the magnitude of the Fourier transform, which, remember, in its most general case is a complex. The Fourier transform is a complex transform. Take the magnitude of the Fourier transform and square it, and that gives us the power spectrum. So one thing that sometimes people don't remember is that the power spectrum can also be found from the autocorrelation function. In fact, the power spectrum is actually the Fourier transform of the autocorrelation function. And that can be derived if you go back to the definition for the autocorrelation function and you insert the integral in place here for rxx of tau, then indeed you do find that that these two expressions are the same. So this is an important thing to keep in mind for later. When we come back and talk a little more about the power spectrum, we will come back to this concept that the power spectrum can be found from the Fourier transform of the autocorrelation function. Because the autocorrelation function is always even, sometimes it's more convenient to do the integral over cosine functions. Not always, but sometimes. And certainly when we are doing a summation, it's sometimes also easier to do the summation over cosine functions. If you don't do the summation over cosine functions, then you need to shift your data and incorporate the negative sum so that you have real functions that you've done the sum over. So for now, the thing to remember is that this integral works for continuous time and that the power spectrum is basically the Fourier transform magnitude squared. So there is an error in the book's equation. This is the equation that the book shows for the power spectrum in terms of the discrete autocorrelation function. It's inaccurate. First of all, the sum would have to have negative terms in n, and notice we're missing a j in the exponent. Let's come back to that. Sorry about that. Notice we're missing a j in the exponent. Also, the sum would have to be symmetric about 0, so that you have both positive and negative imaginary exponential terms in order to get real trigonometric functions out of the sum. Okay, so that brings us to spectral estimation. Now, because the signals that we deal with are a finite sample of a physical process, the best we ever get is an estimate of the spectrum. Now remember that if we have n samples, the frequency resolution is 1 over nt, where t is the sampling rate. Ways to improve resolution in frequency space. One is you can have a smaller value of sampling rate. The other is you can have a smaller value of n, the number of samples. So given a sampling rate, which is usually, we have signals that we deal with after the fact, so the sampling rate is already fixed. The thing that we have to play with is n, the number of samples. So one approach is to segment the data into smaller pieces. Find the spectrum for each piece and then average the spectra. The other advantage that this offers is it does reduce the effects of windowing, because it spreads out the windowing effect over a number of segments, and typically one or more of your segments will allow you to view the data near the middle of the window. So this technique is known as the Welch method of spectral estimation. So just to illustrate this schematically, I have a set of data here over 1 second, and you can see that this has been divided into 3 segments and they overlap. So segment 1 goes from 0 to 0.5, segment 2 goes from 0.25 to 0.75, segment 3 goes from 0.5 to 1. And in this particular example, there, notice, is a 50% overlap between segments. So if you were to just kind of visualize that these data were windowed, if they were windowed with the some kind of Hamming or Chebyshev window in the time domain, then in segment 1 you would of course have your data zeroed out at 0 and 0.5. But notice in segment 2, your data at 0.5 would be right in the middle of the window, and so there wouldn't be as much of an effect for that segment. So the theory is that you window and segment your data in smaller segments. You both get better frequency resolution, as well as you minimize or spread out or average out the effects of windowing across your data over a longer time period. So we'll show an example of what the Welch method, what a spectrum looks like when the Welch method of spectral estimation is applied, and what are some of the advantages and disadvantages. So in this figure, this consists of 3 MATLAB runs. The first run is Fourier transform of some a band-limited signal between kind of a broadband signal like noise that's been band-limited from 0 to roughly 350 hertz. And then there are 2 higher frequency sinusoids that are added in on either side of 400 hertz. So this is a mixed signal of 2 well-defined frequency lines and then a broadband spectrum. And you can tell when you look at the broadband spectrum that it's very noisy. In the Fourier transform picture, it's very noisy, and you can't really tell, is this some kind of continuous spectrum, or are there individual lines? Is this a mixture of maybe some individual sinusoids with background noise, or is it just, a noisy characteristic? So you can see when you apply the Welch method that it definitely has the effect of smoothing out this broadband signal from 0 to 350, and now you can get a much better indication of the shape of this signal. But notice the trade-off is that the individual spectral lines have been broadened and reduced in magnitude. And in fact, when the Welch method is used with a Chebyshev window, the effect is even more dramatic on the higher frequency spectral lines. You can see that they've almost faded into the background, whereas in the Fourier transform, just the Fourier transform approach, you notice that they're, not an insignificant percentage of the total magnitude of the lines. So the advantage then is that the Welch method gives you a better representation of, because remember, why are we looking at the power spectrum? We really want to know where the power is. We really want to know where the power is in the signal. And so the Welch method gives you a much better indication that you got fairly uniform power in the signal from 0 to about 300 hertz. And if I were guessing how this were filtered, I might guess that if I were to find what's equivalent to 0.707 here and try and superimpose some sort of shape here, I might guess that this is filtered with a cutoff around 300 hertz. You can't tell that at all from this window. So the big advantage is you get good representation of the broadband characteristics. On the other hand, you get rather poor representation of the individual spectral lines. So once again, the use of the Welch method is certainly, like many things that we look at in here, a trade-off.